Hi, welcome back. Um, we have just been talking about different ways in which a model can be good. We talked about accuracy, we talked about descriptive realism, we talked about precision, and now we're going to talk about robustness. So think about your simulation process. You've got some input data that you are putting into your model. You use that to create your model. After you simulate, you get some results. All right, and so when we talk about robustness, what we want to know is, let's say that there are some errors in the data. So let's say the data has, maybe there was off by a decimal point, maybe it was collected badly, maybe there's some missing data. There's going to be some error involved in the data. What we want to know is, how does this error propagate through the system? Is it the case that when we run the simulation, we get a much bigger error, or that we get a much smaller error? This is something that's inherent to your model. It's not something you can control, except by changing completely how you decide to model your situation, but it's something to be aware of. We want to know is, if we have some input error and we run the model, we want to know how much error is there going to be on the output from your model. So, for example, let's say our population estimate has an error of 10%. That is, we're saying that we have 5 million, and we're saying that there's an error of 10%, so plus or minus 50,000, 0.05 million. How does that impact the output from our model? Actually, sorry, 5 million was the estimate. That wasn't that was our simulated value. It wasn't our actual population. Remember, our original population was 10 million. So let's say we had 10 million plus or minus 100,000. How is that going to impact our enrollment estimates? Well, when we run our model, 0.05 times p, what do we get? We get 5 million plus or minus 0.05 million. And you can see here that we put in a 10% error, and out came a 10% error. And so this is going to be, we're going to consider this to be a rather robust model. So here's this thing. So is the output error less than 10% or more than 10%? And so what we're going to say is that, if error in is less than or equal to error out, so error out is less than or equal to error in, we're going to say that the model is robust. If it's the other way, if error out is bigger than or equal to error in, we're going to say it's not robust. And again, this is another spectrum here. If the error out is a lot less than the error in, we're going to say the model is very robust. Or if the error out is much bigger than the error in, we're going to say the model is very sensitive to error. So this is just something to be aware of in a model. You might be the situation where you change the data a little bit and your output looks completely different. In that case, you have to be very careful with your model, because your data in has to be really representative of what the real world situation is, or else the output's going to be very, very wrong, very inaccurate. So let's talk about two more examples. So a model is general if it can apply to a variety of situations. So where does our model apply? Our model applies to the set of all students in in the United States. So if you are any particular college, that might not be so helpful, because how are you going to be able to predict how many students you're actually going to have? All you know is how many students there are in the whole country. So if we would like our model to be more general, what we could do is we could decide, oh, let's create a model that works for any campus. Or maybe we will create a model that that doesn't just work for 1 year, it works for 10 years. So, or maybe it's not going to just model how many students come to campus, but also how many want to live in the dorms, or how many classes of mathematical modeling we need to run. So we can make our model more general by addressing more situations and not just one specific piece of information. Of course, the more general you make your model, possibly the less accurate it is for any one of those situations. So in general, it's probably better if you make a more precise model that answers the question that you care about, a more general model, a less general model that answers the uh, the question you care about, and not a more general model that seems to answer the life universe and everything, because that might not be able to actually answer the question you care about. Last, let's talk about fruitfulness. Rather similar to generality, in that when we talk about a model being fruitful, what we're talking about is whether its conclusions are useful and whether it inspires other good models. So if we're talking about this college enrollment model, we could say that it's fruitful because it allows us to plan for demand, for educational grants, dorm space, teacher hiring, courses that you want to run. It's giving information that can be useful for a lot of different types of things. But you could also talk about using this model as a basis for other models. For example, let's say we wanted to talk about removing cars from the roads. Well, we could talk about how many are going to be taken and put in the junkyard in a given year. In that case, the cars play the role of people. Some percentage of them are going to be taken out of commission every year. And if you partition by age of cars, then you're going to get better results. You're going to say the older cars are more likely to be taken out of commission, whereas newer cars are more likely to be able to stay on the road for longer. All right, so we've gotten through our 6 different types of models, but I wanted to say one last thing about accuracy and the advantage of inaccuracy. So accuracy can be very expensive. If you wanted to make your model really, really, really good, you need to collect really, really, really good data. You need to understand all the things underlying the situation really, really, really well. And then you need to create a simulation that took everything into account. All of those things are very expensive. They're expensive because people are expensive. You as a mathematical modeler, you are expensive. Labor is expensive. Also, it takes a lot of money to collect data. It takes a lot of money to do the research to find the underlying understanding. So accuracy is very expensive. So another example of this is the traveling salesman problem. Let's say you have a whole bunch of cities that you want to visit, and you want to find the shortest path that visits each of the cities and gets back to where you started. So if you did that, you might get something that looks like this. And this is a classic problem from computer science, what is the shortest path that gets you from the initial point to the end point in the shortest amount of time? Um, and if you have a lot of locations, there's a computer algorithm that will give you an answer that is a good answer, but not perfect. And it's a fast algorithm. But the other thing you could do is you could run a computer program that gives you the exact answer, but it takes a long time, and it takes a lot of computer power to solve that problem. So there's a trade-off. Do you want a slightly better answer for more expenses? And so that's a cost-benefit analysis that you'd have to do. It'll depend on who you are and what your scale is. So if you end up visiting the same places every day, run the expensive model once. Save money in the long run. If you visit different places every day, run the expensive algorithm daily. So every day you have some different doctor's appointments. You'll go to the doctor's appointment. It'll take however long it takes. You'll take that short route to go and visit those cities, and then those doctor's offices, and then you come back home. You don't have to worry about doing that every single day. On the other hand, if you're UPS or FedEx, you're going to hire some mathematicians or some computer programmers, because you actually saving 5% every day saves 5% of gas, 5% of labor. That's a huge expense that you'll be able to save. And so if for those companies, for people who go to a lot of different places every day, it makes a lot of sense to do that, to run an expensive algorithm, because it's worth it in the long run. All right, so now we've gotten an idea of 6 different ways in which a model can be good. See what you can say about your own model. All right, take care.